Okay, so in the previous section, we used an example to show that the area under a curve over some interval, it was the interval 0 to 1 in that example, can be approximated using these rectangles, these approximating rectangles. And then we showed that if we take the limit as the number of those approximating, as the number of those approximating rectangles goes to infinity, that limit gives us an exact area under the curve. And so what we want to do is generalize this and take it from that one example into the more general case. So let's suppose that we have some curve given by a function y equals f of x, and we're interested in finding the area under that curve over some interval a, b. Now for this section, we're going to be assuming that the curve, whatever curve we're trying to find the area under, is always going to be completely above the x-axis. Because if you think about it, it doesn't sound right if I see the area under the curve when the curve is below the x-axis, because the area would actually go above that curve. In section 5.2, we'll make sense of curves that are not always above the x-axis, because they don't need to be for this concept. But for now, that's the assumption we're going to be making. So we're looking at finding the area under the curve y equals f of x over the closed interval a, b. And the trick to doing this is going to be taking that entire interval AB and subdividing it into n equally lengthed subintervals. And that's what we're seeing here. Those determine these little smaller regions. So we're partitioning the large region up into these n smaller regions so that we can add those areas up. Okay? The subintervals are going to be denoted by x0, x1, x1, x2. So we're seeing that x1, x2, x2, x3, and so on and so forth. And all the way out to xn minus 1, xn, and x0, the left endpoint of the first interval, is equal to a, so it's the same as the left endpoint of my original interval ab. Xn, my extreme right endpoint, is equal to b, okay? So those values are equal to each other. Now, what is the width of each of these subintervals going to be? Well, we're going to denote the width of each subinterval, which will become the base of each approximating rectangle, by delta x, okay? But we can find a formula for delta x, because the total length of the interval AB would just be b minus a, and then we're cutting that up into n equal pieces, which would give me b minus a over n. Delta x, the width of each subinterval, is equal to b minus a over n, okay? And with that, we can also find the exact value of each of these other endpoints in my subinterval. So for example, my left endpoint here, which is x0, is equal to a, but then what would be x1, the right endpoint of this interval? Well, if my left endpoint is a, then to get to my right endpoint, I would have to add the width of that interval, which is delta x. So x1 is equal to a plus delta x. To get to my second value here, x2, so the right endpoint of my second interval, I could start at a and add 2 widths of those subintervals, a plus 2 delta x, and so on and so forth. x3 would be equal to a plus 3 delta x, or generally speaking, if I want the right endpoint of the ith subinterval, which is xi, it would be a plus I delta x, okay? So now what I need to do is find a way of approximating this area up here using rectangles. And I'm going to start with the right endpoint method. So what that means is I want to find the length and width of each rectangle, multiply them to get the area, and then add all of those areas. The length of each subrectangle is delta x, or sorry, width. Let's call it width. The width of each subrectangle is delta x, because that's the length of each of these intervals down here, these subintervals. The height of each rectangle comes from taking my right endpoint. So for my first rectangle, it's going to be x1, plugging it into the function to get the y coordinate of this point. That would be the same as the height of this rectangle. So the area of my first rectangle is f of x1, that's the height of the rectangle, times delta x, that's the base of the rectangle. My next rectangle is going to be f of x2, height, times delta x, width, and so on and so forth, all the way down to the very last one, which would be f of xn, remember that's equal to b, so that's the right endpoint here, times delta x. This is the general formula for finding the approximation using the right endpoint method. We tend to use right endpoints more than left endpoints because the computation is easier. If we let n go to infinity in that definition, then we get the exact area under that curve. So this leads to this definition. The area A of the region S that we showed in that previous image that lies under the graph of the continuous function f is the limit of the sum of the areas of the approximating rectangles. The limit as n goes to infinity of Rn, which is equal to the limit as n goes to infinity of that big sum that we just showed on the previous page. We can show, it can be proven, that this limit will always exist as long as the function f is continuous. In fact, there are even cases where there can be discontinuities and it still exists, but we're not going to worry too much about that. That's of more like theoretical importance. So we used right endpoints, but we could have also used left endpoints, and that would have still given us a correct area. The only difference is that by starting at the left endpoints, the first number you're going to see plugged into your function f of x is not going to be x1, it's going to be x naught, because that would be the left endpoint of that first interval. And then x1, and then all the way up to xn minus 1, because that would be the left endpoint of the final interval, subinterval in that partition that we created. But there's a different way of going about it as well. There's actually no reason why we need to use left endpoints or right endpoints when determining the areas of these rectangles. In fact, each subinterval, so for example, if we take the ith subinterval, xi minus 1 to xi, which in this picture is down here, we could actually just pick any number in that interval. It doesn't have to be the left endpoint or the right endpoint. We could pick anything in that interval, plug it into our function, and use that to determine the height of our rectangle. And that would still be a valid method. So we're going to use this notation. Xi star is going to represent a number that was chosen from this closed interval. It could be one of the endpoints. It could be something strictly between the endpoints. It doesn't matter. It's just any number that we choose in that little subinterval there. That xi star we're going to call a sample point. And so what that does is that leads to this more general definition. The area under the curve could also be written this way. The limit as n goes to infinity of f of x1 star delta x plus f of x2 star delta x plus so on and so forth, where the x1 star, x2 star, and so on are sample points chosen in each of those subintervals. So for example, the first subinterval is x naught to x1 or a to x1, same thing. x1 star might be chosen here, for example. Notice it's not equal to either endpoint. It's pretty close to the left endpoint. But if we plug that into our function, follow this dashed line up, it's going to give me a rectangle that starts at this point. I'm going to put a horizontal line through that point that spans the length of this subinterval. So it's just like a parallel line to here, and then use that to create a rectangle. x2 star just has to be some number in the interval x1, x2. So this one looks like it might have been chosen to be a midpoint of that interval. It was plugged in, gives me a corresponding point on the curve. I put a horizontal line through that and then use it to create a rectangle. x3 star looks like it was chosen a little bit closer to the right endpoint than the left endpoint. It was plugged into the function, used to create a rectangle. So all of these sample points were chosen seemingly at random, but each one is used to determine the height of those rectangles. And as long as I take the limit as n goes to infinity of this sum, I still get the same area that I would have gotten using either right or left endpoints. Okay? Now, a quick note here, and this is also of more theoretical importance. It shows up in some proofs and things like that. The concept of lower sums and upper sums. So if you were to choose those sample points, the xi stars, in such a way that it always produced a minimum of our function. Remember in chapter 4 we talked about minimum and maximum values. Suppose you chose your sample point so that it was always giving you a minimum of that function on the subinterval that the sample point came from. You might get something that looks like this. So look at these rectangles. Here on this first subinterval, if you look at the points on the curve along that subinterval, this point right here is the smallest one. On this next subinterval here, if you look at the curve, the minimum value on that subinterval for this curve is right here. And then this left endpoint of this interval appears to be the lowest or the smallest value on the function on this subinterval, and so on and so forth. We call this a lower sum when we evaluate or when we approximate our area using these smaller rectangles. Lower meaning smaller, right? So that lower sum is giving me the smallest possible area approximation for this curve on the interval AB with a specific number of rectangles. So for 5 rectangles in this case, this will give me the smallest possible area on this curve over the interval AB. Upper sums are defined in a similar way. If instead of choosing the smallest possible value, the minimum on each subinterval, if I choose the maximum on each subinterval, then my rectangles are going to completely over approximate that area. So we call that an upper sum. Okay, we'll do more with this concept in part 3.